Okay. So today we will start with week 5. Okay. So in week 5, mainly we are going to see about transformations from R2 to R2 and the composition of transformations and some relations based on the composition. After this, we will be introducing eigenvalues and eigenvectors for operators from R2 to R2. Okay, so these are the main topics of week 5. Today we will try to cover the first part, that is the composition of linear transformations, and if we have some time then we will try to introduce a little bit about eigenvalues as well. Okay, fine. So let us consider a transformation T from R2 to R2. Okay, so you know that if you have the matrix representation like this, so it will be a 2 by 2 matrix, right? And the range and null are defined in this way, right? So either you have AU or TU, it does not matter. So here you can have either AU or TU. Okay, fine. Now you see that range of T is TU for set of all U in R2. Similarly, null is set of all U in R2 such that AU or TU is equal to 0. Now what is the dimension of this range space? This is both of them are subspaces we have seen, and the dimension of range is rank and the dimension of null space is nullity, right? Rank of T also denotes the number of linearly independent rows or columns of A, right? Can anyone remember what is the relation between range and null or rank and nullity?
Rank plus nullity equal to 2.
Yes, and that is called the fundamental theorem, right, of linear algebra.
Yes, ma'am.
Good, good, very good. Okay, so here is a quick check on your understanding. So consider this matrix, okay, which represents a linear transformation S. Okay, what is the dimension of the range space of S? Anyone? Anyone? So remember that dimension of range space of S is same as rank of A, because A is the matrix representation of S. Now can you tell me what's the answer? Yes, good, Vishal. Anyone else? How many of you agree with this answer? Raise your hands. Those who agree with this answer. Good. Good. Only two. What about the others? You don't know the answer? Okay. So here you one quick check is that what is the relation between rank and determinant? Can anyone tell the relation between rank and determinant? What is the relation? So let us say A is an n cross n matrix. Okay. Now, for an n cross n matrix, rank of A is equal to n if and only if, what can you say about the determinant? What can you say about the determinant?
Not equal to 0.
Good. So it should be not equal to 0, right? So here we see that the rank is 2. Okay. That you can also see, you can either look at the columns. You can see that the first column cannot be written as a multiple of the second column. That is one thing. Or the row. Okay. That is one way. Or the other way is that quickly look at what is the determinant. Determinant of A is 12 plus 12, 24. So it is non-zero. and hence you can say rank is 2. So this is another way, but this can be, this property can be used only for full rank matrices. But yeah, in that case you know that this is useful. Okay, fine. And rank nullity theorem is what we already saw. Rank of T plus nullity should be equal to 2, right? So because of this, if the range is plane, then the null should be origin, and if the range is a line, then the null should be a line, and if the range is origin, and the null should be a plane, right? Because what is the dimension of a plane? What is the dimension of a plane? What is the dimension? Yeah, dimension is 2. Good. So what is the dimension of a line?
1.
1. And origin 0.
0.
So you can see that if dimension of range is 2, then null should have dimension 0, hence it should be origin. And here if the dimension of range is 1, then the null also should have dimension 1. 1 means it should be a line. Similarly, for origin it should be the plane, right? So this comes from the rank nullity theorem, right? Okay. Now consider a linear transformation S from R2 to R2. Which of the following can be the range and null space of S? So we have to use this property we saw here. Okay. So now range is given as x plus y equal to 0, and null is given as x minus y is equal to 0. Now can you tell me what is the dimension of range here? Dimension of range. Can you tell me?
Ma'am, 1
Yes, because it is a line. Good.
line. Yes, ma'am.
Dimension of null. Let's write it for each case. So for A, it is 1. Dimension of range is 1 and null is
Also 1.
1. So is this possible? Yes.
Yes, yes.
Shonali, any questions?
Just a quick question that till which week you will discuss today in today class?
Only week 5. Fine? Okay. Fine. So this is possible or not? Yes or no? So this is possible, right? Because 1 plus 1 is 2, and line, if this is a line, and this can also be a line. So this is possible, right? Okay, this is possible. What about the next one? Because here 1 plus 1 is 2. What about the second B option? What is the dimension of range?
That is 2.
2. And the null?
Null is 1. Then it is
Is it?
not possible.
Yes, it is not possible, right? What about option C?
That is 0.
And null, dimension of null is
Also 0.
0. So again, this is
Not possible.
not possible. And what about the last option? What is the dimension of range?
2. 2 plus 0, it is possible then.
Yeah. So this is possible, right? So only A and D are the possible options for range and null, right? The others are not possible. Okay. So the other important thing we have seen is that suppose W is a subspace of R2 and T from R2 to R2 is a linear transformation, then dimension of T of W is less than or equal to dimension of W. Okay. So the range of this W under T has dimension less than or equal to dimension of W. Okay. Fine. So okay. Consider the matrix M of T 1 minus 1 1 1, which represents a linear transformation T. Determine the output subspace of T when the input is the line x plus 2y equal to 0. Yes, Anand? Tell me a question. questions? Okay. Okay, so for this question, how are we going to check what is the output for the input line x plus 2y equal to 0? See, when you have x plus 2y is equal to 0, so we are considering the set of all x comma y such that x plus 2y equal to 0, right? So if x plus 2y equal to 0, then you know that your y is minus x by 2, right? So because of this, we can rewrite, so this is your input. The set of all x comma y such that y is equal to minus x by 2, or you can simply write x comma minus x by 2 x in R, right? So now how to check the output? Any idea from anyone? It's okay even if it's wrong, you can try your suggestion. Okay, so you see that how do you get a general output? Suppose you have, let's say T is a linear transformation from R2 to R2, and you are having is the matrix representation, right? So checking T of x comma y is equivalent to doing AXY, right? Yeah. So how do you, if so this is the input, so here x comma y is your input and T of x comma y together is your output, right? So here this is your input and you want to check what is T of x comma y. So for that you can also check A of x comma y, right? So you want to find what is T of x comma minus x by 2. So instead we are only given the information about the matrix. So let's use the matrix. So what are we getting? We are getting here x minus x by 2 and here minus x plus, oh no, it's not plus, it's also minus. Minus x by 2. Okay, so here what is the property it is satisfying, we have to check. So let us call this alpha and this as beta. What is the relation between these two? Can you check? What is the equation which combines these two? If this is your alpha and this is your beta, what can you do? So this is, if this way is complicated, maybe I can suggest another way. So here you can take a basis element. Can anyone tell what is the basis from here?
1 and minus of.
Yes. So you can take, so x into 1 comma minus 1 by 2 x in R. So we are not having any fractions here. So we can get rid of fractions here also. So you can have x times of minus 2 comma 1 x in R. So you can use this minus 2 comma 1 as a basis for input. Now what is T of minus 2 comma 1? Just you see this and you will get a quicker answer. This is also correct, but here you may have to do some extra work. So maybe this is easier. So you get, what's the answer here? Can you tell what's the output vector?
Minus 2 plus 1. 3 minus 3. 3 minus 1.
What's the first value?
3.
3. Are you sure?
Yeah. 2 minus 2 into minus 1. That is 2 plus 1.
3 minus 1, ma'am.
3 minus 1.
It's 3 minus 1. Okay. So for minus 2, 1, it's 3 minus 1. Is this correct? But 1 minus 1, 1. Did I make any mistake here? I just multiplied minus 2
That
here.
is 2 minus 1. X
Did I make any mistake? I'm just
2 minus 1. This is
so I have multiplied minus 2 on both sides, so it's correct
okay.
only.
Okay.
So it's correct. So it's minus 2 comma 1, and when I multiply minus 2 comma, okay, that minus I have put here by mistake. That's why the mistake. The minus is here. No one pointed out this one. Now can you tell me the answer?
It's minus 1, comma 3.
Yeah, it's minus 1 comma 3. Now can you tell for which equation this vector satisfies?
Option D.
Option
D.
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 D. See here you see that for first one minus 1, maybe I use blue, the same color. So you see that minus 1 plus 3 times of 3 is not equal to 0. And then 2 minus 1 plus 3 is not equal to 0. Then 3 times of minus 1 plus 3. What about this?
3
This
plus
is
2,
equal to
7.
0. Oh, 3x plus y.
So some of you said option D. Let's check that also. Is this equal to 0?
No, ma'am.
No.
C is correct.
So option C is correct. Okay. So option C is correct. You can also verify that 3 alpha plus beta will be 0. Okay. You can cross check that 3 alpha plus beta will be 0 when you use this. Okay. Maybe this is a lengthier route. So maybe this is an easier way to find the solution. Is this clear? Okay.
Yes,
Fine.
ma'am.
Okay. So for this input line, the output line is this. Okay. So let me ask another question. So suppose, let us say your uh, okay, any line I'm giving, you don't know what is the line. Okay, any line I'm giving, I'm asking what is the dimension of the output space. Let me repeat my question. Okay, so I'm saying that your input your input is a line. It's a line. Find the maximum dimension of output under T, under this same scenario, under T. If input is a line, what can be the maximum dimension of output?
Ma'am, it will be also 1.
Can it be less than 1? Is it not possible to be less than 1? Can't it be 0? Yes or no?
Yes, ma'am, it can be.
It can be, right? Because take
Yeah.
for example the zero transformation. Okay, so that is why here you have this result. Suppose W is a subspace of R2 and T is from R2 to R2. Dimension of T of W is less than or equal to dimension of W. Here dimension of W is 1, so dimension of T of W can be either equal or less than the dimension of W. Okay, so the answer is 1. Okay, so it is so you see that the dimension of output is actually less than or equal to 1. This means that dimension of output is less than or equal to 1. Clear? Okay,
Yes,
fine.
ma'am.
Okay, So now we are moving to composition of linear transformations. So it is exactly similar to composition of functions. In math 1, you have done composition of functions and the properties, right? Yes or no? You
Yes, ma'am.
forgot? Okay, good. Got some answer, please. Okay, now we are having two transformation. S from R2 to R2 and T from R2 to R2 is another transformation. Okay, and we are having their respective matrix representation. Okay, now what is the matrix represent? Imagine that these two are functions only. Okay, so what is the matrix? First of all, what is S composition T? I have not mentioned, but I guess you know. So S composition T means, so S of T of X, okay, is it? So S composition, maybe S composition T of X is equal to S of T of X. Okay, S of T of X. This is the definition of S composition T of X. Okay, fine. All right. So here you see that the matrix representation of S composition T is simply the product of these two matrices AB. Okay, fine. Now, how is the range and null space of this S composition T defined? So, range of S composition T, the usual definition is S of T of V, right? Where V is in R2. But what is TV? What is TV? So what is this set? Set of all T of V such that V is in R2. Can anyone say what is this set? Anyone? Is it that difficult? This was the very first thing we started with today. What is this set? Set of,
TX, T,
yeah? Sorry, what?
TX.
What is your answer? I'm asking what is this set? Set of all T of V such that V is in R2. If you don't know this, then understanding the concepts which have been done so far and whatever we are going to do so far is not going to make sense. I want an answer, at least do some search and tell me an answer. Otherwise, there is no point to continue. This is what we have been seeing. You should know what is this set at least. Good. Thank you. Thank you. At least one answer is there. Good. So it is the range of what? Range of T. Right? So this is nothing but the definition of range of T is this, right? Set of all TV such that V is in R2, right? So we see that instead of TV V in R2, we can replace it with set of all V such that V is in range of, okay? Set of all V such that V is in range of T. All right? Okay. So null of S composition T is set of all V in R2 such that S of T of V equal to 0. Okay. Now S of T of V equal to 0. What is null of S here? So if TV is S of T of V equal to 0, then you can see that TV belongs to null of S. Because what is the definition of null of S? Can anyone tell? What is the definition of null of S? Set of all V in R2 such that, complete this. Yeah. What is the null of S?
that T of B also belongs to null space.
No, just the definition of null of S.
Ma'am, TV equal to 0.
Here I am talking about null of S. Your answer was correct, but remember that we are talking about null of S, not null of T. Yeah? Just the definition I'm asking. So it is SV equal to 0, right? That's all is the definition, right? Yeah? So the definition is set of all V in R2 such that SV equal to 0. Here you see that sorry. So here you see that this TV, suppose so S of TV equal to 0. So TV belongs to null of S. That is correct. But the definition of null of S is this, right? V in RT such that SV equal to 0. So now in place of V, you have TV. So you see that TV belongs to null of S. Okay. So do you understand the definition of range and null of S composition T written in this way? Is the definition clear to everyone? Yes? Yes or no?
What you have written that S of D is equals to 0.
What is the definition of null space then? What is the definition of null space? So null of T is set of all U in R2, that's the TU equal to 0. So instead of T, I have S. So I should have SU equal to 0, right? What's the doubt in that? That is the definition of null, right? Is that clear?
Yes, ma'am.
Okay. All right. Okay. So this note we are going to see in detail later on. So let's not worry about the note right at this moment. I have given the detailed explanation of this later on. We'll see it that time. Before that, so here, what happens when the rank of S and T are both 2? What happens when the rank of S and T are 2? What can you say about the rank of rank and nullity of S composition T when rank of S and rank of T equal to 2? Okay. So remember that what is the matrix representation of S composition T? Can anyone tell? Yeah. What is the matrix representation of S composition T? It's on the same page. The answer. The matrix representation. Yeah. Someone said
Okay,
something.
that is
AB null.
A and B.
A into B. Right?
Yeah.
The product AB. Okay. So now rank of S and rank of T are 2. So what can you say about the matrix A and the matrix B? I have already given you this statement. You know that if A is an n by n matrix, rank of A equal to n if and only if determinant of A is non-zero. Okay. So now can you tell? The rank is 2. So what should be the determinant of A and what is the determinant of B?
Both are not equal to 0.
Yes, both are not equal to 0. So if both are not equal to 0, what can you say about determinant of A, B?
That should also be not equals to
Not
0.
equal to 0.
So we have not yet seen this property, but yeah. So this should be not equal to 0. Okay. So you can see that determinant of A, B is not equal to 0. And if this is non-zero, again you use the reverse direction. If the determinant is non-zero, you use this direction. Then what can you conclude about the rank of the matrix? The rank of the matrix should be,
N.
in this case, what is your n?
2. 2.
2.
2, right? So it means now what you know. So the rank of S composition T is 2. So if rank of S composition T is 2, what can you say about nullity? What can you say about nullity?
0.
Okay, fine. So you see that when the rank of both S and T are 2, then rank of S composition T is also 2 and nullity of S composition T is 0. Okay, this case is clear for everyone, right? Yeah? Okay.
Yes, ma'am. Clear.
Moving to the next case. Now we have only one condition, rank of T equal to 2. We don't know anything about rank of S. Then what can we say? Okay. Note that range of S composition T is equal to S of range of T. Why is that so? So range of S composition T. So here you see S composition T is S of T of V, where V is in range of T. So all the elements here are in range of T. It means what? So the input here is range of T. How did I write it like this? Do you all understand? Because here the input are nothing but the elements from range of T. So I have written S of range of T. Is this fine for everyone? Yeah?
Yes, ma'am.
Okay. So range of S composition T is equal to S of range of T. Okay. And what is range of T when rank is 2? What is range of T when rank of T is 2?
Also 2.
See, range is a subspace. Range is a subspace. Rank is the dimension of the subspace. Which subspace of R2 has dimension 2? Which subspace of R2 has dimension 2? Range of T is a subspace and it is given that the dimension of the subspace is 2. So what should be the range? Then I have to go back to the very first lecture regarding vector spaces. So what are all the subspaces of R2? Yes, what are all the subspaces of R2? Yeah, quiz 2 is coming. Sorry, quiz 1 is coming. You should all remember these things. Yeah, what should be the range? Anyone?
Ma'am, it will be 2.
See, it is a subspace. Can just the number 2 be a subspace?
Okay, okay, okay.
What are all the subspaces of R2? We saw in the beginning of this session also. Like, what are the possible spaces for range and null? Now, can you tell me the answer?
Ma'am, entire plane R square. That is.
Yes. Yes. Good. Stage is good. And also, who was the other person who answered? I don't see your name. Is it Soma? Right? Good.
Yes, ma'am.
Good. Good. Okay. So here it is entire R2. Right? So the subspaces of R2 are R2, line, and origin. Lines passing through origin and origin. Only these are the three possible subspaces. And the subspace with dimension 2 is R2 only. So the range of T should be R2 when rank of T equal to 2. Right? So range of T, I'm replacing it with R2. Okay. Now what is S of R2? So S of R2, how can we write this? S of V, V in R2. Now, what is this set? Can anyone tell? What is this set?
This is range of S.
Yes. So, this is range of S, right? That's why S of R2 is written as range of S. So, what did we get? Range of S composition T is equal to range of S, right? So, it means their corresponding dimension should also be same. So, you see that rank of S composition T is equal to rank of S. Okay, so if rank of T is equal to 2, then the rank of S composition T will be same as rank of S. If rank of S is 2, then it will be 2. If it is 1, if it is it can be 1, or 0 means 0. So it will be just the rank of S. Now what about the nullity of S composition 2? We can use simply rank nullity theorem to give the answer, right? You know that if you apply rank nullity theorem to S composition 2, then T, then rank of S composition T plus nullity of S composition T should be 2. Now, I'm just rewriting the equation in this way, bringing rank to the other side. Now, rank of S composition T is same as rank of S, and again applying rank nullity theorem to S, it should be null of S. So, null of S composition T is equal to null of S. So, if rank of T equal to 2, then rank of S composition T is rank of S, and nullity of S composition T is nullity of S. Is that clear? Is this clear?
Yes, ma'am.
Okay, fine. So now we will see some relation between uh, the composition and the transformations in terms of matrices. So we will see, look at the relation between the null space column space of AB with the null space or column space of A or B. Okay. So what is the column space of AB? It is a set of all ABX such that X is in R2. So this is the same as range of S composition T, right? And this is the same as null of S composition T, null space of AB, right? Okay. Now in terms of matrix, some things are easier to visualize. Suppose B is invertible. Suppose B is invertible, what can you say about the column spaces? So if B is invertible, if B is invertible, what do you know? So you know first of all that set of all Bx such that X is in R2 is R2. How is this so? What is this set first of all? Can anyone tell what is this set? Right? Range of B, right? So if B is invertible, what should be the range? So if B is invertible, first of all, what should be the rank of B? B is a 2 cross 2 matrix and B is given to be invertible. So what should be the rank of B? B is a 2 by 2 matrix and it is invertible. So invertible means what is the determinant? Yeah?
Determinant should be not be equals to 0.
Yes. Determinant is not equal to 0. If determinant is
So
not 0,
rank is equals to 2.
yes, rank is 2. Right? Good. So if rank is 2, then range should be, just now we saw this, right? If rank is 2, then the range should be R2. Right? So same way rank of B equal to 2. So the range of B should be R2. Okay. So this is the first property, first observation from because B is invertible. Now, what is the column space of AB? It is a set of all ABX such that X is in R2. Right? Now, I can write it in this way. Why is that so? Why is that so? It is because here you see that, so consider AY, maybe I'll write here only. So consider ay y in R2. Now if y is in R2, you look at this relation. If y is in R2, then y belongs to this set. Correct? Then y belongs to this set of all bx, such that x is in R2. Right? So this means that y equal to bx for some x in R2. Is that correct? Yeah? You all understand this? Why y is equal to bx? Do you all understand? Yes or no? Why are we able to write any y in R2 as y is equal to bx for some x in R2? Is that clear?
Yes, ma'am.
Okay. So you can see that this ay, the set ay such that y is in R2 can be replaced with set of all a bx. So y is replaced with bx and your x is in R2. Okay. So you see that these two sets are same. And what is the first set? First set is the column space of AB and the second set is the column space of A. Okay. So when B is invertible, the column space of AB is equal to column space of A. Okay. Fine. All right. So this is what exactly we saw in terms of transformation. Range of S composition T is same as range of S. So that is now in terms of matrices, column space of AB is same as column space of A. Okay. So these two are same. This and this. Okay. Fine. The next thing is that if A is invertible, okay, if A is invertible, then what can you say about the null spaces? If A is invertible, okay, first of all, what are we doing? If AB and ABX is equal to 0, we can multiply A inverse on both sides, then BX is equal to 0. Okay, null space of AB equal to null space of B. Why is that so? From here, null space of AB equal to null space of B. How is that so? So first here we have started with an element X from null space of AB, right? And then here we saw that X belongs to null of B. So if X belongs to null of B implies X belongs to null of B, what does it say? From this, what is the set inequality you can get from this implication? X belongs to null of AB implies X belongs to null of B. What is that you will get from here? What is the set inequality you will get from here? What is the relation between null of AB and null of B from here? This is a basic.
X equal to 0, then Bx.
Yeah, Bx equal to 0. I'm asking what will be the relation between null of AB and null of B. What I have proved, if I take any element from the null of B, then it should also be in null of B. What does that mean? Which set is containing which?
Means null of B is the subspace of AB.
You are saying the other way around. Because see, suppose let us say this is a set X. This is a set Y. Now, which is a subset of which?
Agree, ma'am. It's null of B is the subspace of null of.
So you see here, first of all, Y. What happened?
Y is subspace of A.
Y is a subset of
A. X.
right? So this means what? For every element here, for every element here, it will also be in X, right? This is the meaning of this, right?
Yes, ma'am.
So here you see X in null of AB implies X in null of B means null of AB subset of null of B. What about the other way around? So if you take any element X in null of B, what do you know? According to the definition, Bx is equal to,
0.
okay. So what happens to ABX then?
It should also be 0.
Then this means that X belongs to null of A, correct? So
Yes,
now we have said X belongs to null of B implies X belongs to null of AB. Now this means that null of B is a subset of null of AB. So if null of AB is a subset of null of B and the other way around is also true, what is the relation between null of AB and null of null of B? What
then
is the
equal,
relation?
then
Yes,
equal to both are equal.
yes. So null space of AB is same as null space of B. Okay. So you see that the null space of AB is same as I guess it is mentioned in terms of nullity. Nullity of S composition T is same as nullity of S. So here you see that, okay, here it is about nullity, here it is about null space. Null space of AB is same as null space of B. Nullity is a different thing. Here we are talking in terms of null space, and here the condition is also different. Here the condition is rank of T equal to 2. Here we are talking about A being invertible. So this we have not done in terms of transformation, only in terms of matrices. Okay, so this is what I have mentioned in note here. Okay, fine. So the explanation for both these part, is that clear for everyone? If you have any doubts, please ask me. Is this part clear, the explanation for both of this? Either you should say yes, or if it is no, you should tell me what's the doubt. If you keep quiet, I don't understand. Here I am the one who don't understand what's going on.
Ma'am, it is clear to me.
Okay, good. Thank you.
It's just a small
Others?
doubt that
Yes, yes, Sonali.
if the null space of AB is equals to null space of B, it
Hmm?
means that the whatever the element which is in the AB should also be in B.
In the null space of AB, yes. So it means what? What does this mean? So if, let us say, any element you take in this set, okay, it will also be in this set. Similarly, if
Okay.
you take any element in this set, it will also be in this set. They both are same. So it means what? If ABX is equal to 0, then BX should also be 0. Similarly, if BX equal to 0, then ABX is also 0. That's all. Clear?
Yes, ma'am.
Okay, good. So in this case, we simply are saying that ABX is equal to 0 if and only if BX is equal to 0. Okay, when A is invertible, this is what we are concluding. Okay, fine. Okay, when is the composition 0? Okay, so the question is, when is S composition T equal to 0? Okay, so the first case is when S or T is 0. Okay, the 0 case. So when both are 0, so when if S is 0 or T is 0, then obviously S composition T should be 0, right? So if S is 0 or T is 0, both should be 0. S composition T should be 0, right? Okay, so this is one trivial case. So suppose let us say rank of S is equal to 2, then S composition T is equal to 0 if and only if T equal to 0. Why is that so? Why is that so? What does it mean if rank of S is equal to S is equal to 2? What does this mean? You can talk
It
in terms of
is into
determinant
two
also.
matrix that is linearly independent. That is 2 into 2 matrix.
The corresponding matrix, yeah, the columns are linearly independent.
Yeah, yeah.
And the determinant is,
Not equal to 0.
yeah. So you see that rank of S is equal to 2 means the corresponding matrix A, determinant of A is non-zero, right? Now, what can you say? Then AB equal to 0. Here we are talking about the entire matrix, so maybe I will not use determinant. That will give some confusion. So let us say that range of S is, what is the range of S? I have already told you. If rank is 2, then what is the range?
Entire plane. That is R square.
Yes, yes, good. Right? So range of S is R2. So if range of S is R2 and you have T equal to 0, then it's obvious that if one of this is 0, then obvious that S composition T is 0. But if S composition T is equal to 0 and range of S is equal to R2, what can you say about T? What can you say about T?
T must be 0.
Yes, right?
Obviously 0.
Yeah, because you see, what is range of S? Range of S is nothing but S of R2, right? S of R2 here. So S of R2 is just again R2, and now here you are having S of T of some value, and that is going to be 0, right? This means that your T should be equal to 0. So here let me write S of Tx equal to 0 for all x. Okay, but range of S is R2. So this means what? Your T must be 0. Your T of x should be 0. Okay, for all x. Otherwise, this cannot happen because the range of S is R2. So here, for non-zero values, it should go to non-zero vectors. Okay, so this has only one option, that T is 0. Okay, similarly, when rank of T equal to 2, the same argument will happen. So S composition T equal to 0 if and only if S is equal to 0. Okay, so these are kind of very intuitive. If you understand it intuitively, it is very clear. Very straightforward things happening here. Okay. The other case, this is kind of non-trivial. These are very trivial to see, but this is non-trivial. Okay. So when both S and T have rank 1, then what will happen? Okay, here both are like here in this case rank of S is 2 and here rank of T is 2. Okay, but what if both are having rank 1? So here is an example. What is the rank of this first matrix?
1.
1. What about
One.
the second one?
It's also one.
Okay, what is the determinant of this matrix? Let's call this A and let's call this B. What is determinant of A?
0.
And determinant of B?
This also 0.
Okay, so you can see that the rank cannot be 2. But how is the rank 1? You just look at the number of linearly independent rows or columns. Okay, here you see only one non-zero row. So straightforward rank is 1. Here you see that column 2 or row 2 is a multiple of, so column 2 is 2 times of column 1. Agreed? Clear, right?
Yes, ma'am.
So you see that only one linearly independent column, so the rank is 1. Okay. Now, what is the matrix representation of S composition T? We already saw it. It should be the product of AB. Now, they are computing the product AB. This is the resulting matrix. And for the resulting matrix also, there is only one non-zero row. So, the rank is again 1. Okay. What is the rank of this matrix AB? So, this is the matrix AB. What is rank of AB?
1.
1. Okay. But is the matrix AB non-zero?
Then it will be 2.
Right? So this matrix is non-zero. All the entries are non-zero. Say not zero. So this means what? There are some non-zero entries. Okay, this is one case. The other case is that we have a similar scenario. Okay, so you have a matrix A, you have a matrix B. Okay, so the rank of A, what is the rank of A?
1.
1.
The rank of B?
That is also 1.
1, because here you see that the second column is 2 times of the first column, right? So rank of B is 1. Now what is A into B? A into B is 0. The matrix is 0 matrix. Okay, so obviously the rank should be, what is the rank of the 0 matrix?
0.
0. Okay, so when rank of S and T both are 1, the resulting matrices can be anything, nothing can be concluded from this. So you see in the first scenario we got a non-zero matrix with rank 1. In the second scenario we got a 0 matrix. So what is the takeaway from here? Product of two non-zero matrices can be all zeros. Okay, so product of two non-zero matrices can be all zeros. We took two non-zero matrix, but still we ended up with a 0 matrix. Okay, fine.
Okay. Yes, yes.
Good. Okay, so an exercise for everyone. Those who are sleeping, wake up. Find the range and null of T composition S. So for that, first compute T composition S and tell me. Everyone, compute first T composition S and tell me what is the transformation T composition S. T composition S of x comma y. So you need to find T of S of x comma y. I'll give you a few minutes. If you have any difficulty after trying for a few minutes, let me know. I'll help you. Oh, sorry, I forgot to unmute. So the final answer is 3y, x minus 3y and 3y minus x. Is it correct? Is that correct?
Yes, ma'am.
All right. Okay. So now find the range and null of T composition S. You can either use the definition of T composition S or you can use the matrix representation of T composition S. The matrix method is what we have already seen. So maybe you can quickly compute the matrix. Using that, you can find the range and null. So what is the matrix representation of T composition S? What is the first column?
X minus 3y.
What is the first column of the matrix?
One minus three.
No. I'm asking the first column, not row.
1 plus 3.
1?
3.
No.
3 means
No. See, what is T composition S of 1, comma 0? What's the answer? 1, comma?
1 comma minus
Minus
1.
1.
Yes, good.
Minus 1.
So what should be the first column then? 1 minus 1, right? What is T composition S of 0, comma 1?
Minus 3, 3.
Minus 3, 3.
Okay. So this is minus 3, 3. Now can you quickly tell me what is range of T composition is? So you see that. So let's say this is the first column. I'm calling it maybe V1 and this is V2 I'm calling. You can see that V2 is minus 3 times of V1. Right? So you can see that this is just span of only V1. Right? Yes or no? So V1 forms a basis for range. Is this fine? Yeah?
Yes,
So,
ma'am.
so you can see that this is set of all alpha comma minus alpha. Okay, if you want to write it in terms of set notation, then you can see that this is set of all span of v1 is alpha times of 1 comma minus 1 alpha in r, so which is alpha comma minus alpha. What does this set represent in R2? Can anyone tell? What does this set represent in R2?
And this is line.
Okay, good. Can you tell me what is the equation of the line? So this is your y, this is your y, and this is your x. What is the relation between x and y? Your y is equal to,
X plus C.
Y equal to minus x.
so this means x plus y equal to,
0. Yes, yes.
okay. Now similarly find the null of T composition S. Right? Is this the line representing null of T composition S?
Yes, ma'am. Line.
Yeah, this is the line. Right? X minus 3y equal to 0. This is your null of T composition S. So the range and null for this transformation, is it clear for everyone? Yes?
Yes, ma'am. Clear.
Fine. So I have given the sets here. So this is the, what is this set? I have given x minus 2, it's x minus 3. So this is the range of decomposition S, and this is the null of decomposition S. Okay, fine. So verify the answer quickly. Consider two matrices A and B representing linear transformations T and S, respectively. Which of the following options are true? Okay, so as a hint, I have done this matrix multiplication for you. Based on the matrix multiplication, you can quickly tell me the answer. What is the range of decomposition S? What is the range of decomposition S?
0, ma'am.
0, right? This should be 0. What about range of S composition T? Is that also 0?
No, ma'am.
No. What is the range of decomposition S? We already saw it to be 0. But what about range of T? Is that also 0?
Yes, ma'am.
Yes. Is the range of T 0?
No, rank is 1. That
See,
is,
range of T is 0 means that your matrix, the corresponding matrix is 0.
Sorry, ma'am. Range of S will be 0.
Range of S, again, range of S is 0 means your matrix B is 0. So now tell me whether the option C is first of all correct or not. You know range of T composition S is 0 because AB is the 0 matrix. This is the 0 matrix actually.
ma'am,
Okay.
range of T is line. So
Yes.
it is T is not equal. This is not wrong.
Yes. So range of T, you can see that, so this is V1 and this is minus 2 V1. So you see that it is span of V1, right? And it is non-zero, right? So you see that it is not equal. What about the last one? Range of S composition T and range of S. What is the range of S composition T? So this you can observe that if this is V1, this is minus 2 V1. So
Yes.
range of S composition T is span of
Yeah.
V1, and your V1 is 24 comma 12, right? And
Yes,
this,
ma'am.
can I write it as span of, so what is the common factor here?
12.
So if I take 12, then it is just 2 comma 1. Can I write it as span of 2 comma 1,
Yes, ma'am.
right? So now let's look at the range of S. So it is, you see, if this is V1, this is minus 3V1, right? So the range of S is span of V1. So this again I can write span of 2 comma 1.
Number 1. Yes.
So now what about option D? Range of S composition T and range of S, are they same or not?
Yes, ma'am. Same.
Same. Is this question clear for everyone? Yeah? All right? Clear?
Ma'am, all right.
Okay. So the next topic here is what are linear operators. Okay. So linear operators are nothing new. They are linear transformations only. Okay. So what are linear transformations? You know that linear transformations satisfy two properties: t of x plus y equal to t of x plus t of y, and t of alpha x equal to alpha times of tx. So the domain and codomain can be any Rn and Rm. So it can be R2 to R, R2 to R3, anything like this. Okay. The domain and codomain are different. Okay. But it can also be same, right? So if the domain and codomain are same, in that case, the linear transformations are called linear operators. That's all. Okay. A linear transformation from the same space to the same space is a linear operator. Okay. So what is a linear operator? So when the domain and codomain are same, then they are linear operators. The transformations are called linear operators. Clear? What is a linear operator? Okay. Now can you quickly tell me which of the following are linear operators? So first quickly tell me what is the domain and codomain in each case. For A, what is the domain? What is the domain for A? The first option, what is the domain of T? Where does x comma y belong to? Where does this element belong to? Which space? Is it that difficult? Is my question not clear? Yeah, it's R2. Good. No, not lying. So your domain is R2. It is just a vector x comma y. It's in R2. Okay. What is the codomain? Is this an element of R2? It is just 3x plus 4y means it is just a number. So where is the number lying in? What is the space? What is the space? Why there is so much silence? Where is 3x plus 4y lying? Is it lying in R, R2, R3, R4? Where is this number lying in? Which space? R2. R2 means what is the first coordinate and what is the second coordinate? R2 means it should have two coordinates. What is the first coordinate and what is the second coordinate? You understand? What's your mistake? Here only one coordinate is there. So what is the codomain then? I want an answer, at least anyone. Is it, I'm even explicitly asking, is it R, R2, R3 or what is that? No, I'm asking what is the codomain. So where does this element belong to? Is it in R, R2, R3 or where is this lying? R2 means you need two coordinates. R3 means three coordinates. R means only just number. I cannot ask this more
Maybe it is
clearly. Yes.
R in
Yes.
R.
Okay, this is what I'm asking. This is in R, right? Okay. So this is a number, so it should be from R. Okay, now can you quickly tell me the answer for the others? What is the domain of option B? Again, R2 and codomain is no.
That is also R2.
Yes, very good. Because two coordinates are there. So R2, R2, very good. What about option C?
R2, R2.
Both will be R2.
Good. What about option D?
R2 again.
Yes. So first option definitely cannot be a linear operator because the domain and codomain are different. For a linear operator, domain and codomain should be same. What about option B? Is this a linear operator?
Yes, ma'am.
Option C?
It's a linear operator.
You-
Option D?
It is also.
There is a check. There is a check. Any linear transformation, if you remember, should be of the form alpha 1x plus beta 1y, alpha 2x plus beta 2y. Is this a linear transformation? Option D, is this a linear transformation?
No.
So you see that you have a product. So this T is not a linear transformation. So option D is not a linear transformation and hence it cannot be a linear operator. So linear operator first of all is a linear transformation and then the domain and codomain should be same. So only option B and C are linear operators. Is that clear? Everyone? Good.
Yes, ma'am.
Good. Okay. Okay. Now suppose T from R2 to R2 is a linear transformation and the matrix representation of T with respect to the canonical basis is A. Okay. So the matrix representation is A. Then for any n in n, T power n is also a linear operator from R2 to R2 and the corresponding matrix is given by A power n. As simple as that. If A is the matrix representation of T, then A power n is a matrix representation of T. And if A is a matrix of order 2 cross 2, what is the size of A power n? What is the size of the matrix A power n? You are multiplying 2 by 2 matrices several times. What is the resulting matrix? Again 2 by 2, right?
Yes.
Yeah. So this is also a 2 by 2 matrix. So you see, if this is an operator, this is also an operator of this from the same domain to codomain as this. And if A is the matrix representation, then A power n is the matrix representation of T power n. Right? Okay. Now, can you try to answer this question? Consider a linear operator T from R2 to R2 defined in this way. Okay. And M of T is the matrix representation of T. Now, first find what is M of T and then find the matrix of T square. So what is M of T? So what is T of 1 comma 0?
3-0.
No.
Oh, 4-0.
No.
0, 3.
Oh,
No.
0,0.
No. My God. I'm happy at least everyone is participating now. Okay. So you put
0,4.
yes, thank you. So it is 3 times of 0 and 4 times of 1. So it is 0 comma 4. Right? Good. What is T of 0 comma 1?
3, 0.
Thank you. Okay. So 0, 4, 3, 0. Okay. So the first option is correct. What is the square of this matrix? Quickly compute the square of this matrix. What is 0, 3, 40 into 0340. Compute this and tell me. What is the first entry?
First is 12.
And then
It is 0.
this entry is 0. This one,
Then 16.
16.
this is
No,
16.
0,
Okay.
0 and 12.
Okay. So you see that this is incorrect. Right? Okay. Now, what is t squared we have to find? So for that, can we quickly compute what is m of t square? Do we already know? This is m of t square, right? M of t whole square is same as m of t square. That is what we saw here. The matrix of t power n is a power n. And what is a power n? A is the matrix of t. So this is the meaning of this, right? M of t power n is m of t whole power n, right? So here m of t whole square is m of t square. So we have the matrix of t square. So if we know the matrix of t square, can we say what is the transformation? What is the transformation? Can we say? So this is the matrix, right? So this is a square. So if this is a square, then a square xy gives you t square xy, right? So which option is correct?
Option D.
Yeah. Okay, fine. Is this problem fine for everyone?
Yes, ma'am.
Okay, good.
Yes, ma'am.
So we are introducing complex vector spaces now. So it is very similar to that of real vector spaces only. Only change is that now the entries can be complex numbers. Okay. So instead of R, everything is now replaced with C. So C2 is set of all x comma y such that x comma y is in C. Okay. And this is a vector space over the scalar field C. Okay. So it means what? All the scalars will be from C. Okay, clearly R2 is a subset of C2. Okay, and all the definitions are same. T from C2 to C2 is a linear operator. Range and null are defined exactly in the same way. All the definitions are exactly same. Only change is that in place of R we are having C, complex numbers. Okay, fine. Okay, so the next topic comes into play. I guess it's good to start the eigenvalues and eigenvectors topic from the next session, but now we have some time. So anyway, I will try to give an introduction. First of all, so far, what are the things we have seen? Just let's make a quick summary. In today's session, we started with range and null space of a linear transformation, right? The definitions are very similar to this, right? And then we saw what is the composition of linear transformation, what is the relation between the range and null of these composition to the null and range of the transformations under the composition, right? And then we also saw the matrix representations and the relation between the matrices, right? So these are the things we have seen initially, and then we saw what are linear operators, right? Only this much we have seen, and then powers of matrices here. Okay, so up to this no doubts, right? Up to this part no doubts, right? Because the next topic is something very important and it's going to be something new apart, it's going to be new from the topics we have seen so far. So far everything clear, right?
Yes, ma'am.
Okay, good. So this is a very important topic. What are eigenvalues and eigenvectors? Okay. So if you say that you have done a course on linear algebra, then definitely there will be questions from eigenvalues and eigenvectors. Okay. So what are eigenvalues and eigenvectors? To understand this, there are some basic things we should know. So let's try to recall. So any three vectors in R2, remember that they are linearly dependent, right? And a linear transformation is invertible. A linear transformation T is invertible if rank of T is equal to 2 or null of T equal to 0, right? And a linear transformation is said to be singular if it's not invertible, that is when the null is 0. Okay. Here there is a mistake. When T is 0, it's said to be invertible. So for not invertible, it's non-zero, right? Null of T is non-zero. Okay. And if T is singular, there is a non-zero vector V such that TV equal to 0. That is exactly what is meant by null of T not equal to 0. Null of T not equal to 0 means what? It contains a non-zero vector. So there is a non-zero vector in null of T. So this means what? There is a V non-zero such that T equal to 0. So these two statements are exactly the same. Okay. Are these statements very clear to everyone? Because this is the basic for the next topic. Is that very clear? If it is not invertible, why there is a non-zero vector in the null space? Is that clear for everyone? Yes or
Ma'am,
no?
can you give in one example?
Okay, sure. See, first of all, why it is non-zero? Can anyone tell? When the transformation is singular, that is not invertible, why the null is 0? Why it has to be non-zero? Okay, I will give you the hint. Use rank.
Because the dominant is not equals to 0.
Determinant is equal to 0, right? See, what's happening here? If T is singular, it means what? It's not invertible. If it's not invertible, then the determinant of A, let's say the matrix of T is A, then the determinant of A is
0.
0.
0.
If the determinant of A is 0, you know that rank of A is what? Can it be 2? Can it be 2?
So then it will be dependent vectors, right?
Yeah, so it should be strictly less than 2, right? It cannot be equal to 2. It should be strictly less than 2. Yes or no?
It could be 1.
Yeah, that's why I'm saying it's less than 2 means so 0 or 1. It can be 0 or 1, right?
Yes.
Yes. So if rank of A is strictly less than 2, so it is either 0 or 1. So what does rank nullity theorem tells you? Rank and nullity. So you know that the sum should be 2. So if rank is less than 2, so it should be either 0 or 1. So if it is 0, what is the nullity?
2,
And if it is 1, what's the nullity?
1.
1.
1.
Then you see that nullity is non-zero. So you see that nullity is non-zero.
Yes,
Now you
ma'am.
understand
Now it
why
is
for
clear.
singular transformation nullity is non-zero. Is that clear now?
Yes, ma'am. Clear.
Yes, ma'am.
And same way for rank of T equal to 2, again the same logic only. 2 plus 0 is 2. So that's why rank of T equal to 2 means null of T equal to 0 here. Okay. Okay. A complex number lambda is said to be an eigenvalue of T if T minus lambda I is singular. Okay. T minus lambda I is singular. What does that mean? What should be the determine if this is singular? what should be the determinant of t minus lambda I?
It will be 0.
It should be 0. Okay, so we say that a complex number lambda is an eigenvalue of t if determinant of t minus lambda I is 0. Okay, such a lambda is the eigenvalue of the matrix M of t. Okay, fine. So determinant of what is mean by t minus lambda I? It means I'm considering the matrix representation of t. Okay, so let's say A minus lambda I, it makes more sense. Okay, fine. So to find the eigenvalues of t, you find the eigenvalues of the matrix A by solving determinant of A minus lambda I equal to 0. Okay, now can anyone uh, did anyone for at least did this thought come to you? Why instead of a real number, why are we saying a complex number? Did anyone think about this? Yeah, why complex number? Why not just real number? Any idea? Okay. What do you, how do you, this determinant of A minus lambda I, how does it look like? If you see that, you will get an idea. Let's say you have a 2 by 2 matrix A, B, C, D. Okay, this is your A. Now, what is determinant of A minus lambda I? It is the determinant of A minus 1, B, C, D minus 1. A minus, lambda, right? Not just I, it's just minus lambda I. So this. Up to this, is this clear what I have done? I've just written a matrix A and then computing determinant of A minus lambda I. This is clear, right? Yes or no?
Yes, ma'am, clear.
Now you see, when you do this determinant, you get something like this. So you end up with lambda square minus A plus D times of lambda minus BC. Is that correct? Yeah? Yes or no? So minus A lambda minus D lambda.
Ma'am, there is another term, AD.
Yeah. AD minus BC. So do you see this as a polynomial in lambda, polynomial of lambda?
Yes, ma'am.
Of degree 2. Okay. Regarding polynomials, what do you know about the solutions of polynomials? Are they always real numbers?
No,
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 ma'am.
right?
be
It
complex
depends on
number.
the discriminant, right? It depends on the discriminant being
Yeah.
positive or negative, right? That
Yes,
is
ma'am.
why, see, what are these eigenvalues? The eigenvalues are roots of this polynomial. So you know that the roots of the polynomial are not restricted to real numbers. It can be complex numbers as well. Hence, we have mentioned that this number is a complex number. Now, do you understand why the word complex comes in this definition instead of a real number? Yes?
Yes, ma'am. Yes, ma'am.
Good.
It's clear.
Okay, there is another important observation. What is the trace of the matrix A? What is the definition of trace? Do you all know? What is the trace of the matrix? Do you all know?
Sum of diagonal elements.
So, what is the trace of A here?
A
For this
plus D.
A plus D. What is the determinant of this matrix?
AD minus BC.
So, what is that you have here? Determinant of A minus lambda I is equal to lambda square minus trace of A times of lambda plus determinant of A. This is a very important observation. It helps you to reduce your time of doing this calculation. Simply compute trace and determinant, then you will get this polynomial. And there is a name for this polynomial. this polynomial, determinant of a minus lambda I, this is called the characteristic polynomial of A. Okay. Yes, Shonali. You have any question?
Yes, ma'am. As you said that the polynomial, the determinant of a minus alpha I is the in the form of the polynomial, right?
Yes.
Which having the degree 2. So,
Yes.
If it is not be the real, then the solution is in the complex. So, in the definition, it's given that a complex number of the lambda. So the solution is always be in the complex number, or it should be also it can be also be a real number.
Okay. So let's say x plus iy. This is a complex number, x comma y in R. This is a complex number. Yes or no?
Yes, ma'am.
Okay. Now let us say real numbers means what are the real numbers? Any number between?
Minus infinity
Plus
to infinity.
infinity to infinity.
Is 0 a real number?
Yes,
Yes,
ma'am.
ma'am.
Okay. So now if y is equal to 0, then my z is x plus iy, which is simply x. Now is z a complex number or a real number? Tell me your answer. Is it a complex number or a real number?
Real number.
Real number.
Is it not a complex number? Is this of the form x plus iy only? Is it not a complex number?
Yes, ma'am, it is.
Yes,
So,
yes.
so you can see that it is also a complex number. So real numbers are subset of complex numbers. So complex number include all the real numbers as well. So if you are saying a number is a complex number, it can be real number, it can be 0, or it can be purely imaginary, or it can be a number of x plus of the form x plus iy, where x and y are non-zero or 0. Okay, so it is basically a complex number means any number of this form which can also include which also includes real number. Do you understand?
Yes, ma'am.
Okay, good.
Thank you, ma'am.
Good. Okay, so let's do these two problems here. Find the eigenvalues of the following matrices. How are we going to find the eigenvalues? First, find the characteristic polynomial. So let's do one. I will do the first problem, you do the second problem. So we have to first find determinant of a minus lambda I. I can either do it using this, or I can use the determinant of the matrix as well. Just for the problem's sake, I will do both. So 3 minus lambda, 1, 1, 3 minus lambda. So this is 3 minus lambda square minus 1. So lambda square minus 6 lambda plus 9 minus 1. So it is lambda square minus 6 lambda plus 8. So you can see that the trace of the matrix is 6 and the determinant of the matrix is 8. Okay, so either way you can compare this. Now, what are the roots of this equation? Can you tell these roots?
4 and 2.
Yeah. So lambda minus 4, lambda minus 2 equal to 0. So lambda is equal to 2 comma 4. Okay. So what are the eigenvalues? 2 and 4 are the eigenvalues of A. So finding eigenvalues, how are we doing? Is that clear for everyone? Yeah? Is this clear?
Yes, ma'am.
Okay, now can you do the same for B? The matrix in B? Yeah, everyone please try for the second problem. For the second matrix 1, 2, minus 2, 2, 5. First, compute the characteristic polynomial and tell me.
Minus, ma'am, delta A minus lambda equal to lambda square minus 6 lambda plus 9.
Lambda square plus
Minus
6
6
lambda.
lambda plus 9.
Correct.
Ma'am, minus 6 lambda
Yes, it's minus. Yeah, sorry.
plus 9.
Lambda will be 3.
Yeah, correct. So lambda, both the eigenvalues are 3. Okay. So these are the eigenvalues of A. Okay. So here you call these eigenvalues as real and distinct. Okay. And these type of eigenvalues are called repeated eigenvalues. Okay. These are real and distinct eigenvalues. And these are repeated eigenvalues. Okay. Is that clear? Just the naming terminologies I have mentioned. So what are eigenvalues, how to find eigenvalues, and how are we classifying the eigenvalues? Is everything clear?
Yes, ma'am, clear.
Okay.
Yes, ma'am.
So let me see whether I can give an eigenvalue where you have complex roots. Just a minute. Okay, let's check this check this matrix. What is the characteristic polynomial for this? What is determinant of A minus lambda I? Yeah.
Ma'am, lambda square plus 1 equal to 0.
So what are the eigenvalues in this case?
Complex number.
What are they?
Plus minus I.
Right? These are the eigenvalues of A. Okay. And you can see that these are complex eigenvalues. Okay. So any of this case can happen. It can be either real and distinct, or it can be repeated, or they can be complex roots as well. Okay. Fine. So with this, we will stop today's session. The next topic is what are eigenvectors, that we will continue in the next session. Okay. So any questions from today's session so far?
Ma'am, next session that is tomorrow.
Yeah.
Okay.
Okay, so thank you everyone. See you all tomorrow.
Thank you, ma'am.
Thank you.
Thank you, ma'am.